Hello everyone, in this video I am going to explain the last isomerism in structural isomerism, that is tautomerism. Tautomerism is also called as desmotropism. So what are tautomers? Tautomers are the isomers which are interconvertible by the transfer of proton, by the transfer of H plus ion between first and third atom. Whatever may be first or third atom, not a carbon, not only a carbon, there may be any atom between 1 and third position, not 1 and third carbon. So what are tautomers? Tautomers are isomers which are formed by interconversion between one and other, interconversion by the transfer of proton. Tautomers are the isomers which are interconvertible by the transfer of proton between 1 and third position. See definition. Isomers which are interconvertible by the transfer of H plus ion between first and third positions in molecule are called tautomers, and the phenomenon of interconversion of isomers is said to be tautomerism. If molecules are interconvertible by the transfer of proton, that phenomenon is said to be tautomerism. Tautomerism is also called as desmotropism. Tautomerism is dynamic isomerism, always changing, so not stable composition, always it is always interconvertible. That is why dynamic isomerism. Say examples or conditions, for example, to show tautomerism, molecules should have the following structural arrangement. Then only tautomerism is possible for the molecule. That is H hydrogen atom that is attached to X atom. I will write here hydrogen atom that is attached to X atom attached to Y atom double bonded with Z atom in this case. Okay, here what is X atom or Y atom? What is X atom or Y atom? Here X and Y atoms are any atoms, there is no condition, any atoms, but Z atom is carbon, otherwise nitrogen, otherwise oxygen, otherwise sulfur atoms only. So X may be any atom that contain one hydrogen, Y may be any atom that is double bonded with Z atom. Z atom must be carbon or nitrogen or oxygen or sulfur. Here Z, only Z for the condition for the only Z necessarily to be carbon, nitrogen, oxygen or sulfur. Here X may be any atom that should contain one hydrogen. This is condition. So take this, I will give examples. Molecules which have this molecular structure, this condition, show tautomerism. Tautomerism is also called as ketoenol isomerism. I will explain. Aldehydes, ketones, nitroalkanes, imines show tautomerism. Aldehydes, ketones, nitroalkanes, imines, etc. show tautomerism. These molecules show tautomerism. See, first aldehydes. I will show tautomerism in aldehydes, that is If you take acetaldehyde, IUPAC name is, what is IUPAC name of acetaldehyde? IUPAC name for acetaldehyde is ethanaldehyde, CH3CHO. If you observe this molecule, it has XYZ structure, X molecule, Y molecule, Z molecule. See, X double bonded with Z or not? Yes, X double bonded with Z here. Okay, and X atom contain hydrogen atom. Possible. Yes, here tautomerism. This tautomerism gives transfer of proton between 1 and 3rd position. This is first position, second position, third position. 1, 3, 1, 3, H plus transfer. 1, 3, H plus transfer. This is called as tautomerism. This phenomenon is transfer of proton from first position to third position is known as tautomerism. So this tautomerism, due to this tautomerism, double bond comes here and this hydrogen goes there. The CH3 becomes CH2, this become double bond. Here O become OH after addition of, after transfer of hydrogen. So this is not ketone, this is keto form. It's a keto form and it is enol form. Keto form, enol form. So tautomers are in the form of keto-enol forms. That's why tautomerism is also called as keto-enol isomerism also. Not necessarily to be a ketone. It is in the form of keto. Keto form, enol form. Okay. Next, taking second example, ketones. For ketones, I will take example acetone. CH3, C double bond O, CH3. So this molecule in the form of XYZ. XYZ or not? Yes, XYZ in the form of XYZ. Here transfer of proton from first position to third position. So due to transfer of proton from first position to third position, same transfer of proton first position to third position, what happened? This proton comes here and double bond shift here, then that give CH3, no change. Here C double bond will become COH and here single bond become double bond, CH3 becomes CH2. Again see, this is keto form, enol form. Ketone, enol. Okay. Next. Third one, in nitroalkane. In nitroalkanes, tautomerism. I am taking this molecule CH3 nitro group. Is this in the form of XYZ or not? XYZ. Yes. X atom contain hydrogen, between Y and Z double bond. 1, 2, 3. This numbering is not numbering of carbon atoms in parent chain. This is just a shift between 1 and 3 position. If they participate in 1, 3 proton transfer, then what happens? This hydrogen comes here between X and Y, double bond form between X and Y. That becomes CH3 becomes CH2, here double bond and double bond. Here hydrogen comes here, it becomes OH. This is same enol form. Not enol, it is in the form of enol and it is in the form of ketone. And last example, imines show keto-enol isomerism. See this example, CH3, CH double bond NH. So once verify, this is X form containing hydrogen. Y form, that may be anything that is double bonded with Z necessarily to be oxygen, carbon or nitrogen. Okay, right. Here transfer of proton possible. So due to transfer of proton, same tautomerism. Due to transfer of proton here between 1 and 3rd position, proton transfer, tautomerism. So by the tautomerism, what will we get? Here CH3 becomes CH2, it becomes double bond. Okay, CH, this becomes single bond, here NH become NH2. NH, by the transfer of proton, NH become NH2. So hydrogen comes here, double bond shifted to there. So this is what amine. This is amine. This is imine. Imines and amines. Enamine. Enoamine. Exactly. Enoamine. Enamine. Imine and enamines are tautomers. Okay. Thus tautomerism possible with the given molecular structure. HX single bond, Y double bonded to Z molecule. So take this. Next I will give some more example. In 2,2-dimethyl propanaldehyde, tautomerism is possible or not. Verify once. Of course, this is Y. Y form is okay. Z form is okay. X form is not okay because X contain no hydrogen atom. So here what you can say, tautomerism not possible. In this molecule, tautomerism not possible. Tautomerism not possible because our X atom contain no hydrogen. If I give this example, benzaldehyde. Benzaldehyde. In benzaldehyde, tautomerism possible or not? Verify. Z atom okay, Y atom okay, X atom. See X atom, for X atom there are hydrogens or not? 1, 2, 3, 4 bond. Carbon with 4 bonds means no more hydrogen, no hydrogen. So here also what you can say, tautomerism not possible. Tautomerism not possible. So if you take this example, third one, benzophenone. In benzophenone, tautomerism possible or not? Benzophenone, tautomerism possible or not? Not possible. Here Z atom okay, Y atom okay, X atom contain no hydrogen. For this is also X atom, no hydrogen. So we can say, we can clearly say tautomerism is not possible. If you see other example, 2-phenyl ethanol, 2-phenyl ethanol. For this molecule, tautomerism possible or not? See Z atom okay, Y atom okay. For X atom, hydrogens are present. Yes, possible. X atom contain hydrogen atom. So Y atom, between Y and Z, double bond is there. Okay. At Z atom, oxygen possible. Here tautomerism is possible. Tautomerism possible. Okay, then transfer proton from X to Y. Phenyl group same, no change. Here CH, double bond C, OH here, and this is H. See, proton transfer to here and double bond shifted here. Enol form, keto form. Yes, possible here. Take this. Next, if you take acetophenone, tautomerism possible or not? Verify. Z atom okay, Y atom okay. For X atom there are no hydrogen. For X atom 1, 2, 3, 4 bond. 4 bonds means no hydrogen. No hydrogen means tautomerism not possible. Not possible or possible? Possible. If you take this is X atom. So YZ, X, XYZ possible or not? Yes, X atom containing hydrogen. Here tautomerism possible. Tautomerism possible. Tautomerism. So due to this tautomerism, here phenyl group, no change. Hydrogen comes here and it becomes double bond. Enol form, keto form, enol form. Tautomerism possible. If you take this molecule, tautomerism possible or not? Yes. Z atom, oxygen clear. Y atom between Y and Z okay. Here this is X atom, this is X atom. Here how many hydrogen? 1 hydrogen. Here 2 hydrogen. Always shift hydrogen from here to here. If from Y atom to X atom to Z atom, then what will you get? Your double bond already there. Here transfer from proton from here to here. But this content is very less. Very less. This is much more. Interconvertible, but almost 99% exist in this form only. Only 1 or less than 1%. Less than 1% exist in this form. Very less. This is because ketoenol content always depends upon stability. This is reason very less stable. Very less stable. Here this is more stable. This is what? More stable. Thus, here I need to explain one concept. Ketoenol content. Okay, take this. I will explain what is ketoenol content, how it depends. In general, keto form is greater percentage than enol form. If there is no special factor, there is no effect. In general, keto form is always greater than enol form. In sometimes enol form may be greater. When mainly ketoenol content, keto or enol content, ketoenol content mainly depends on stability. Mainly depends on stability of a molecule. If enol form is more stable, enol is more content, keto form is more stable, definitely keto form will be more content. Okay, so stability stability of molecule. Stability depends on stability of molecule depends on the following factors. Depends on the following factors. First of all, we need to verify where aromaticity is present or not. If aromaticity present, that is 100% more content, very dominating one. First verify for aromaticity. Next, it depends on hydrogen bonding is present or not. If aromaticity not present, then verify for hydrogen bonding. If hydrogen bonding is not present, then verify for conjugation. These concepts we will learn in next videos. Next, solvent can also affect ketoenol content. Okay, here domination, aromaticity more dominated than hydrogen bonding, than conjugation, than solvent. Solvent has very little amount of effect. Aromaticity affect the percentage of composition. So example. So I am not going to explain here what is aromaticity. Aromaticity is a separate topic, out of 15 topics in basics of organic chemistry. One of the topic is aromaticity. I will explain in next videos. So here, if you see this keto form, this form. So here Z atom, Y atom, X atom contain 2 hydrogen. Only 2 bonds for this carbon, 2 more hydrogens. Possible or not? Yes, possible. Here transfer of proton from 1 to 3rd position, tautomerism, definitely possible. Then here that form converted to here double bond, okay. Here proton transfer from X to Z, then Z getting hydrogen between X and Y, double bond. So this is not aromatic, non-aromatic, but this is aromatic. So more stable, aromatic, so more stable. This is less stable. Aromatic, so more stable. I will explain what is aromaticity, what are aromatic, anti-aromatic, non-aromatic. I will explain. So therefore this is more percentage. This is less percentage. Always exist in this form because this molecule getting stability like that. Okay, take this. How hydrogen bonding affect ketoenol content, ketoenol percentage. Next is, if you take this example, HCO and here CH2 and here C double bond OH. Okay, so for this ketoenol, Z atom, okay, Z atom, carbon, oxygen, nitrogen or sulfur, oxygen, okay. Y atom, okay, between Y and Z double bond, okay. This is X atom containing hydrogen. Okay, tautomerism possible, clearly possible. Tautomerism possible. Tautomerism means transfer of proton between 1 and 3 position. So from X position to Z position. If transfer of proton takes place, here Z getting hydrogen and between X and Y double bond, CH2 becomes CH and this is same. See here, hydrogen atom attached to more electronegative atom that become partial positive between partial positive hydrogen and more electronegative atom, hydrogen bonding is there. Here hydrogen bonding possible. That's why this is more stable, always more percentage. Thus this is obviously less percentage. Why is it less percentage? Less stable. Okay. Next, if you see acetyl acetone, CH3, C double bond O, CH2, C double bond O, CH3. Okay. Next, here enol form CH3, COH, double bond CH, single bond C double bond O, CH. Here hydrogen bonding possible, but in polar protic solvents, so not dominating character is not here. Here in polar protic solvent, this is more content, almost 80%, 20%. Of course, hydrogen bonding is possible. Hydrogen bonding not dominating over solvent, that is wrong concept. So in solvent, so we can say this point. In polar protic solvents, that aromaticity dominated over hydrogen bonding and conjugation, but between hydrogen bonding and solvent there is no competition, no domination. So here solvent, in polar protic solvent, keto form is more content, keto form is more stable. What are keto forms? What are polar protic solvents? Polar means bonds between heteroatom, polar bonds, and protic means they have hydrogen atom. Polar protic solvents, example H2O polar protic solvent, between hydrogen and oxygen, polar bond, different electronegative atoms attached with each other, definitely polar. Hydrogen is partial positive and oxygen is partial negative. Polar, hydrogen is present, protic, polar protic. The CH3, CH2, OH, ethanol also polar protic solvent. Acetic acid, CH3, C double bond O, OH, acetic acid also polar protic solvent. In polar protic solvent, remember this point, keto form is more stable than enol form. So here, if we learn conjugation concept and aromaticity concept, this keto-enol content will be very easy to understand. So this is here it is not possible to explain aromaticity, because to explain aromaticity, bond polarization effects, resonance effect, mesomeric effect are important. Okay, so take this one. Hope you understood well. Thank you.